That was silly.
Who thinks I should bleach the tips of my beard, make
If
it
you
blonde?
make it white,
I really like it. It looked like you had snow on your beard.
It's like a reverse Backstreet Boys.
if you add white and add a red top hat, you would be Santa.
Yeah, I actually did that
Santa Dan is
one
our
year.
Santa.
I tricked my son into thinking that I was Santa.
What?
Yeah, it was hilarious. I'll tell you the story at the end today if we've got time. Okay.
Okay.
He was really little. He was like 2. Okay. Okay, here's our warm-up question. Um, so it's in Pear Deck itself. Okay. So you
Okay.
want to make sure that you get in there. So there's that link one more time. But tectonic plates interact in different ways depending on the type of boundary between them. Okay, right? So the way that they meet and what's happening where they meet determines what they do. Well, that makes sense. Okay. So which of the statements is essentially a correct definition? We've got a convergent boundary, a divergent boundary, a transform boundary, and another convergent boundary. Okay, as options. Um, Option A is that at a convergent boundary, plates move apart, which creates new ocean floor. Option B is at a divergent boundary, plates slide past each other, which creates a big fault. Um, Option C is a transform boundary, and that's stating that plates collide. So and that forms mountains. And then option D would be convergent boundary again, and this time it's saying that plates move toward each other, causing the buildup of mountains. Oh, squirrels are cool. Squirrels are really cool. They are essentially furry. They're essentially slightly dumber rats with furry tails. Um, Rats are actually incredibly highly intelligent. Squirrels are not as smart as rats, and a large reason for that is because we have been breeding rats in labs for hundreds of years, making them smarter.
Oh, really? So rats are not scientists?
Rats are not scientists? No, no. Some scientists are rats, though.
Sorry, I was making a joke.
Yeah. Orion, what's up? Oh, you got your answer?
Yes.
Okay, which one do you think it is?
I believe it is the last question, the very bottom answer.
Yeah,
Convergent boundary plants move towards each other, causing subduction or mountain building.
perfect. You are
Although I do
absolutely
know
correct.
that most boundaries hit the ground of the ocean, but I wonder if it does affect the ocean, then does it also affect the tide? A bit of the water
Oh,
too?
that's a great question. So if these boundaries affect the oceans, do they also affect the tides? Sort of, sort of. They don't really affect the movement of the tides, but they can affect the level of the tide when it's at high and low tide.
Because I wanted to answer this question because I did this a couple of days ago. It's about earthquake
Mhm.
that we're going to talk about. So I thought if the boundaries happen with the earthquakes, kind of like helps the earthquakes make the tsunamis.
Yes. Yeah, so all of them, well, we'll look at the data. We're going to look at the data. So we're going to look at the data pretty early here. We've got a couple other questions here that we're going to check in on. Evie, what's your question?
I was gonna say I've also done this on like Tuesday.
Mm.
So yeah, I've pretty much remembered what a convention um, boundary was or whatever it was called again.
A convergent boundary, yeah.
Convergent. Thank you. I was
Awesome.
mixing up convection and a conversion. Convection
Well,
is mostly with heat and
yes.
yeah, temperature.
So it all
Correct, you
comes down
are.
to that con word at the beginning, right? And I'm glad you pointed that out. So you're confusing those two words because of that prefix we would call it, right? And the way language is structured, at least our language, Indo-European languages. So basically, any language from that's sourced from India to the end of Europe, anything that comes from any of those have the same roots, okay, and they have a tendency to work very similarly together. And so we have what's called suffixes and prefixes, right? So prefixes go at the beginning of the word, right? Suffixes go at the end of a word, and they change or add on to a word's meaning. And scientists, right? Scientists are efficient. We're going to say efficient, okay? Some might call us lazy, but we want to know what we're doing. We want to know what we're looking at just by looking at it, right? So we try to name stuff in a really obvious way. So we adhere to those language norms, those using prefixes that people know. In English, it starts to get confusing because we borrow from a lot of different languages. They're all part of that Indo-European language group, but um, they branch off fairly early there. And so we've got prefixes from Greek and prefixes from Latin that sound the same, that may even be spelled the same, but mean something different. So
Right.
it can get very confusing in English.
Yeah. Okay. Yeah. Like, it just gets confusing sometimes.
Yeah, it can, absolutely. Um, So, why is Earth's inner core solid? It looks like all of you, everybody who's responded, is saying it's because of the pressure from the layers above. That is 100% it. There's just so much stuff on top of it that it's smashing it all together. Okay. So, which layer is made up of the tectonic plates
Hmm.
or the rocks underneath the continents and oceans? Or Ryan, I'm guessing you've got your answer here.
I usually do get my answers quite quickly. Lithosphere.
Yes, the lithosphere. That's what most,
Yes.
probably two-thirds of the people in the Pear Deck are writing down. That's excellent. In fact, let's look at those words. Litho is short for lithography or lithograph. Oh, well, that's not okay. Well, that will help us with this here. Lithograph, a lithographic print. That is not helpful. Here, let's look up. Let's see. Litho prefix meaning. Okay. The prefix litho comes from the Greek word lithos, meaning stone or rock. Check it out. Okay. So
I can see the
the mesosphere, meso actually is the prefix that means middle. Okay. Which of the following describes what Earth's core is made up of and why it has that composition? Okay, so we got a couple different responses here. They're pretty long, so I'm not going to read them out this time. Um, I'll summarize them. Okay, so we want a description um, of what Earth's core is made of and why. Okay, so option A says it's made of iron and silicon because they're the least dense. Option B says it's made of oxygen and silicon because they're the most dense. And option C said it's made of iron and nickel because they are the most dense. So which one is it? Orion, what do you say?
It is made of iron and nickel.
Yes. And it's because they are some of the densest materials that
And they're
make up
also
Earth.
some of the most known elements that help make up our Earth.
What do you mean by most known?
Well, we all know that gold and is more founded, but it's not as useful for the elements that helped create our Earth. And
Well,
also,
they have different use applications.
Okay, that is true.
you know. So all the elements do they interact with each other very differently, and they interact with nature differently, and so they have a lot of different applications, most of which are incredibly useful. But yes, iron is one we use a lot of, right? There's a lot of it here. Um, we use a lot of it. It's in every piece of steel, right?
True.
And steel makes up large
But I
portions
have
of our
one
cities and
question.
buildings. Yeah.
Um, if iron is thing that help it make buildings, how does it make up like rock and stone in our Earth though?
Wait, say that one more time.
If if iron is like the thing that helps us make our buildings and stuff, how does it make up the thing that we stand on today?
Oh, good question. So, most of that iron and nickel that is part of Earth is down at the center, it's down at the core. But there's so much of it that some of it is up here in the crust, in the lithosphere. So, it can be in two places, right? The same atom can't be in two places at once, but we've got lots and lots of atoms. It's just that much of it. That's a good question. That's a really good question, Ryan. Okay, so today we're really going to look at that evidence that all of these scientists used to solidify, see what I did there, the theory of plate tectonics, right? We talked about Alfred Wegener and continental drift and how he couldn't really explain how the continents move, which is one of the big reasons why nobody took him too seriously. Um, because he didn't have an explanation for how it happens. So we're going to look at the evidence they use to help prove that his ideas were fairly correct. That it is the continents that are moving. Okay. So here's a question for you. Are continents the same thing as tectonic plates? What do you guys think? Like we know we've got 7 continents here on Earth, right? I love that you guys are popping up with your hands. I'm going to let a few more people answer in Pear Deck before we vocalize. Ooh, we seem fairly split here in Pear Deck. Okay. Adeline, what do you say?
No, they're not the same, but sometimes the continents line up with tectonic plates.
Oh, so you're saying they're not the same thing, but sometimes they line up. Orion, what do you say?
Well, that is true, Adeline. I believe you there, but I also believe yes, because they all are like the continents. We all know they are pieces. We can see that they all once fit to one another, and tectonic plates do the same. They just
Mm,
move over time
okay.
and
I,
change in different directions and cause things that we feel today.
so Orion, you're saying they aren't the same, but they're kind of the same. Is that right?
Yes, they're more
Okay.
like they have the same properties.
Okay. Let's dig into that, guys. Let's dig in. Let's look at some of this evidence. So, what you need to do is go open up the apply it, the modeling boundary movement apply it for this week. Okay. You can click on that link in Pear Deck. It is there. Hopefully, you already have one open. Here's mine, right? Well, it is mine. I don't know why I put quotes up there. I'm going to zoom in a little bit. Okay. So we're going to look at data. And the reason we're looking at data is because that's what scientists do. We are taking a shortcut because we're not going to spend the next 20 years gathering the data, which is sometimes how long it takes. But we are going to look at the data that has been gathered by others. So sometimes some scientists spend a lot of time gathering data and then they analyze it. There's actually a lot of scientists out there that just look at data that has been gathered by other people. And then there's other scientists that look at the analysis of the data that other people do. It's called a metadata research. And what they do is they look at thousands upon thousands of research journals and articles, and all of the conclusions that were drawn and all of the data there, and they put it all together. It's pretty interesting. Okay. So we're going to look at each of these maps. Okay. Each of these maps tells us something different, and we are going to identify at least two patterns that we notice on each map. So I'm just going to sit here. Let's see if it'll, yep. I'm
What do
just
you
going to
mean by patterns?
open. So what is a pattern? Let's start with that. What is a pattern, guys?
A pattern is something they have the same thing of, like is like something that happens in a specific order. Specific, sorry, I'm trying to say.
Okay. It's stuff that kind of goes together, right?
Yes.
Yeah. Okay. And so a pattern, it shows up it shows up differently in different situations, right? A pattern in fabric is not necessarily the same thing as a pattern in the stock market, right? But we can follow, like we can look back and we can see what things we're doing, right? And patterns, identifying patterns allows us to predict what might happen in the future, right? It's a pattern is that identifiable shape, essentially. Okay. So let's look. We're going to start with this elevation map. Okay. So this first one is this elevation map. Okay. And elevation, yes, Azalea, yes, something that repeats. Okay. Patterns have a tendency to have repeating natures. Okay. So elevation is the height of something above sea level. Okay. So on this map, we've got the key down here in the bottom left. It's a little hard to see, but I'll summarize it. Dark blue is the lowest elevation. Gray and white are the highest elevation. Oh, thank you. Thank you, Adeline. And, we've got in between, the scale from dark blue all the way up to white. Green is sea level. Okay. So green, something that's green we would consider flat land that's at the same point as the ocean sits. Okay. And now, if you stop and think about it, the ocean is really just a big puddle of water. Right? You pour water onto a surface, it's gonna clump together and it's gonna fill the lower points. Okay. And if there's walls on the side, it's going to be held in. Well, you can think of the higher points as big walls on the sides of the bowl that is Earth. Okay. So if we look here, what's a pattern you guys see here? Somebody, well, I'll do this one. I'm sorry. I'm noticing that a lot of these really high places, right? These reds, these whites, um, these grays, those are the really, really high places. They tend to be on the coast, right? They tend to be on the edge of a continent or ocean, right? That's where I'm seeing really high places here on the continents. So I'm going to write that down. Okay. So here we go. Most of the areas of high elevation are along coastlines. Okay. I might want to add specificity. I see your hand, Evie, just a second. Most of the areas of high elevation, I'm going to add specificity on continents or on land. I'll say on land or, yeah, on land are along coastlines. So near the edge where the land and water meet, right? That's what a coastline is. Evie, what's up?
I was gonna say, I also noticed that a lot of the red is on Antarctica. If you look down here.
Yes, a lot of the red is down on Antarctica. Now, I'm not going to write that one down. And the reason I'm not going to write that down is because we've got this special situation happening in Antarctica. Antarctica is unlike anywhere else because it is so cold. There's no liquid water on
Right,
the
that's just something
surface.
that's just something I spotted. That's my fault.
Yeah. Oh, no, no, no. You notice something really, really, really important. That's an important piece of data. Okay, that almost all of Antarctica is high elevation. Okay. It turns out it's because there's so much water frozen there. Literally miles of frozen water on top of the land at Antarctica. And it's because it's so cold. So it's just so cold that we can't see where the dips and the rises are really because there's just like any dips that there would have been are filled in with water and frozen. So it's a very very good observation, Evie, and it's definitely something that normally we would write that down, we'd set it to the side, we'd say we're going to have to investigate this, figure this out. We're not going to do that today just because of our limited time. Another piece, another pattern that I noticed on here is that in the oceans, right? I know this is an ocean. I've been looking at maps my whole life. I know that these areas, these blue areas, are where there's ocean and water, right? And it makes sense that those would be the lowest areas because that's where the water flows down to, right? And it sits in the lowest areas. But there's some higher areas here in the oceans. And it looks like they form lines, like distinct lines, right? Hmm. So I said there are areas of higher elevation within the ocean under the water. Okay. So our observations of patterns don't have to be super profound. They don't have to be something crazy, right? I said on land, high elevation along the coast. That's where I see a lot of it. And in the water, there's some high elevation and some low elevation, some very distinct high elevation points, right? So let's look at some of these other maps, and you're going to tell me the patterns you see. You can put it in chat. You can unmute yourself. Um, doesn't really matter. However you want to tell us. Okay. So our next map that we're going to look at is this one, the thickness of the Earth's crust. Okay. So this is this is measuring how thick it is if we were to drill from where the air touches the ground all the way down until we hit the asthenosphere, the next layer, right? So all of this is solid rock. Okay. What patterns are we seeing here with how thick the crust is? Ooh, Azalea noticed that we see the thinnest stuff near the coasts. You are so, so, so close there, Azalea. Um, but she noticed that we see thinnest stuff near the coast, or at least on land, we see thin near the coast and thicker as we get towards the center of those big chunks of land or the continents. Okay, let's write that down. Okay, so on land, the crust is thinnest near the coast and thickest near the near the I'm going to say the middle or farthest from the coast, right? We can say the middle, the center, the point is that it's the farthest, it's the points that are farthest away from the water. Okay, that's a fantastic observation. Now, Azalea made an interesting statement that I did the same thing the first time I looked at this map, and a lot of people do. I want to see if anybody pieces it together. Orion, what's a pattern you've seen?
A pattern I see is that near Asia, Japan, and Europe, there's a lot there than the others.
What do you mean by a lot there? You mean thicker crust?
Yeah, way thicker crust than everywhere else.
Okay.
But
So it does seem like that, right?
yes.
That's a good observation. There seems to be thicker crust here, right? We do have even thicker, maybe right here in South America. Um, That's definitely something we'd want to write down. I'm let's write it down. Let's write it down. Okay, so
Evie also has her hand out too.
there appears to be thicker or more thick crust under the Eurasian continent, right, than anywhere else, than any other continents. Okay. And there's one really key detail that I think we're all overlooking, and I know why we are. Evie, what's the pattern you see?
I was gonna say, I think Orion may be talking about the little red spot.
Are you talking about just the little red spot or kind of all of this,
Like
Orion?
pretty much all this. There's like a red spot in the middle.
Yeah.
Over here.
Mostly all of it.
Okay.
Also, there is one more thing else I see.
Yeah.
Is that
What is
all
it?
of these places, they all have like good amount of crust in them, but it's like the whole planet has enough crust, but there is no crust in the ocean at
Ooh,
all.
you
I mean,
are
there is. It's literally the ocean. Of course, there's no crust in it.
Actually, there is at the bottom of the ocean.
yes. So
Oh yeah.
something is holding up that water, right? If we look at these lines, this is what we would call a
I think
topographical
that's
map.
what we missed.
Okay. That is
Yes, it was
exactly what we
like
missed. Okay. So,
I looked at the map carefully. Wait a second.
yeah. If we look at these lines, they each represent a level of elevation. Well, this line right here, the outermost line that we see at the continents, is a line of 10, representing a thickness of 10 kilometers. That means everything inside that line is thicker than 10 kilometers, and everything outside that line is thinner than 10 kilometers. So there's crust out here. It's just thinner than 10 kilometers.
And we could not see it because the crust is shown. They technically left it invisible
Well,
for
all of
us.
this is representing crust, right? This is
Yeah.
representing just the crust and its thickness. So even though even though it's less than 10 kilometers thick, it's still there. There's still rock there. Okay, so something I've noticed is that it seems to be fairly uniform in thickness under the water, right? On land, we've got some really high points and some really low points, and we've got a lot of variation in thickness. But under the water, it's all really thin, right? I'm going to put that down as our third observation. The crust under the oceans is fairly uniform in thickness. Actually, let's make that one. And then the crust under the oceans is almost all under 10 kilometers thick. So it's pretty thin as far as the crust goes. Now, 10 kilometers thick, that's 7 miles, guys. That's not a small distance. Okay, let's look at the next one. Mid-ocean ridges and ocean trenches. Okay. So ocean trenches are these dark spots that I've tried to point out here. You see that where these red arrows are pointing? And ocean ridges are these dark spots that look like they're peaked upwards. Evie, what's a pattern you see?
it kind of looks like those trenches are little circling around. Looks like Africa.
Oh, that is not Africa. Africa's over here. That is actually the Pacific Ocean. But that's a really good observation. Okay, I'm going to say many of the visible trenches are surround the Pacific Ocean. So that's going to be where the deepest, like the deeper they are, the easier they're going to be to see on this map, right? Because we are looking at the whole globe. Orion, what's a pattern you see?
all of it is very close to all the edge of every single continent, especially the Pacific Ocean. The main black, you can see all of them look like they circle almost all of the bottom below of the continents.
So you're saying that there's that we see a drastic elevation or
Yes,
okay, so a drastic elevation change on the edge of the continents?
yes.
Okay. That's good. It's a good observation. We've already made that one though, looking at the elevation map. What about the ridges? What do you guys see any patterns with the ridges? Yes, Adeline.
They seem to be a bit higher. The coastlines looks like, especially in the Pacific Ocean.
Oh, so they look like they're significantly higher in elevation than the rest of the ocean floor. Is
Yeah,
that what you're
along the
saying?
coast of
Okay.
like North America and South America in the Pacific Ocean.
Okay. So we're gonna say the ridges look, let's see, we're gonna say are higher in elevation than the ocean floor surrounding them and appear to even be higher than parts of the continents. That's what you're noticing, you said? Is that right? Okay. Awesome. You guys are making fantastic observations. Keep them coming. Azalea's sending me a lot of these same ones here in chat, right? She also knows those really thick areas in Asia and in South America. Okay, so let's look at our next map. Ooh, heat flow. Hmm. Hmm. Here we've color coded this. Okay. Around the edges, those are actually longitude and latitude degrees. But if we look at the legend down here at the bottom, heat flow, there's more heat where it's red, and where it's purple, there's less heat. Okay. So the more purple and blue it is, the cooler it is. The more red it is, the hotter it is. So what do you guys notice? Let's think of it about these other maps we've looked at. Are there connections here, maybe? Orion, what do you see? You got your hand up?
I see that most of the world is definitely cooler than that
Oh,
area of the ocean, and that's near
okay.
I'm trying to remember what ocean that's near. The red is near one of the most major near one of the oceans, like a main area of the ocean
Okay.
of one of the oceans.
So we're going to try to stick with one observation per person. Let other people jump in here. So I'm going to write down the first one you said, which was the most of the crust is pretty cool. It's fairly cool. And then I've got an observation in chat here, which is the same as what you were starting to say there. And that is the places of highest heat flow appear to follow the ocean ridges. So if I were to take this map and put it on top of that ocean ridge map, I
Ah,
bet
I see
that
it.
these heat flows would sit right on top of those ocean ridges. That is a phenomenal observation and connection there. Well done, Azalea. Okay, here's one of crustal age. We're not going to dig too much into this one, just because we're running low on time. So we're going to look at it, but we're not going to write down our observations. I'm going to let you guys do that, okay? Um, but there's a couple interesting patterns going on here. This one is crustal age, but just the ocean. Okay. And you can see here we've got numbers in our scale. Um, those represent how many millions of years ago this rock formed, solidified. Okay. Down here, it has the name of the geologic eon or era that these things formed in. You can look that stuff up if you want to, but basically the orange, like the bottom one there, Archean, that's the oldest. And as you go up in that scale of colors there, that light yellow at the top would be the youngest. Okay. So where do we see the youngest ocean here, guys? Where's the youngest ocean floor, Adeline?
Towards the middle of the ocean, like sometimes farther away from the continents.
Ooh, okay. So we're seeing a lot of that young ocean in the middle, or rather, a lot of that young crust, ocean floor in the middle of the oceans. Okay. Young oceanic crust is in middle of oceans, farthest from continents. Okay. Young ocean crust, if we again go back and look at the young ocean crust, that seems to line up with that heat flow map, doesn't it? With those ridges. Okay, young ocean crust appears to align with ocean ridges. Okay, now, probably in my mind, the most interesting maps we're going to see, and these are live maps. This is live data, guys, which means this is being tracked in real time. This is the United States Geological Survey, USGS, okay, an arm of the federal government, okay, that tracks earthquakes and talks with other agencies around the world that track earthquakes. And this is a list of all the earthquakes that have happened in the last day that were at least a 2.5 or above in magnitude. Okay, so I'm going to zoom in a little bit. Okay, look at that. Now, if I go, let's see, magnitude. Let's see, it's giving me the newest first. Let's see if I can change the setting here. I want to go 30 days, anything over 2.5. Holy cow. There's so many. I know, Adeline, right? They're happening all over the
Are
place.
those
Now,
people?
no, these are earthquakes.
That's a lot of earthquakes. From the way they look lined up, if that continues on the places at the edge of those lines, it's gonna cause massive damage and split more of the continent.
It could. Now, these are earthquakes. Everything shown here is an earthquake bigger than a 2.5 magnitude. If you were directly above an earthquake, so most earthquakes happen deep in the ground, right? If there was one that was, say, 5 miles down, directly below where you are sitting, you probably wouldn't feel it unless it was over a 3.0. Okay. So 2.5 is pretty small. Not really something we're going to feel. Now
If it
that,
was the strongest earthquake, I feel like
mhm.
that if we were on top of that earthquake 5 miles down, it would cause more damage to the top and most likely kill us.
Well, it really depends. There's a lot of information that goes into it. We're going to talk a lot about earthquakes next week. But what do we notice about the patterns here of the earthquakes? We've got somebody noticing that that a lot of them are happening here around the Pacific Ocean. Orion, what do you notice about their pattern?
I noticed that they're all on the edge of every single continent I see.
Ooh, we
In
tend to see them. Yeah.
see, especially more specific oceans, they're right on the edge of every single one of them.
Yes, we are seeing them on the edge of continents. On the
Not like in the center where everyone else usually lives. So it means earthquakes are more away from all of us
Mhm.
than we expect them to be.
Well, where they are in relation to where humans live is a different issue entirely. We have a tendency to live where it's easier to live,
Yeah,
right?
true,
Where we
but
can
I
grow
am right.
food and transport stuff. But here we're seeing a lot of earthquakes on the edge of continents here, right? I do see your hands, Lacey and Adeline. Lacey, I'm gonna go to you. What is the pattern you see? I see your hand, Lacey, but okay, Adeline, what about you?
Sorry, I had to zoom out again.
No, that's okay.
Um, I've noticed that they're all kind of clustered into certain areas and they're not really spread out.
Oh, okay. So they cluster. They tend to happen in around the same place. Yes, Lacey, go. Unmute yourself. Go. Oh, okay. If you type into the chat, I'll say what you write. We've got some microphone issues.
That part is in the Pacific Ocean. It's called the Ring of Fire, right? And that's where the tectonic plates meet.
Ooh, so
Exactly right.
it turns out that's how we
True.
know where they meet. Let's look at the volcanoes. Okay, if we look at a volcano map, zoom in on that. And we're going to look at all volcanoes. Holy cow. That's a lot of volcanoes, guys.
And look, they're still around the Pacific Ocean. Still, there's more of them there.
Look,
That's
they're
where the
in the
Ring of
same
Fire is.
places.
Ah,
What? So we're seeing the earthquakes and the volcanoes
in the same place.
and the ocean ridges all in the same places. Okay, so I would write some of that down. Okay, so what patterns do we notice? Okay, in relation to the plate boundaries. Okay, so if we look at this map, this is a map showing us where the tectonic plates meet. And the reason we know where these plates meet is because of all of this evidence. We can feel earthquakes. We can look at volcanoes. We can go measure a fault, right? We can see these things and feel them and hear them. And we've come to the conclusion that
Teacher, the pear deck isn't working for me. It keeps showing a different side than what we're on. It's stuck on 8 for some reason.
yeah, so we haven't gone farther in the pear deck. These are all links from the show it that we're looking at. Okay. So we know where these boundaries are because of all of that physical evidence. And it turns out that these big plates, there are chunks of the Earth's surface that move together. It's really hard to notice that when you have to walk everywhere, right? Where it takes an hour to go a mile and a half, which is why this is fairly new. The theory of plate tectonics is only 60 years old, guys, because we've been looking at everything from our tiny human perspective. But now that we can communicate with everybody in the world, now that we can all share the things we've noticed and measured and seen and heard, now that we can fly up into the sky and look down from really high above, we can see these patterns. It's really cool, the stuff we are noticing and finding out in science and geology specifically that we couldn't before because we just didn't have enough pieces. didn't have enough pieces of the puzzle. So tectonic plates came about because we were able to see all those pieces. Okay, so you're going to look at these other maps, okay, and look at the various types of plate boundaries. You're going to notice where they are and answer these questions for the show it. Okay, we're not going to get to that today. There are some vocab terms. We're pretty much out of time at this point. So you can stick around and I'll answer more questions, but I do want to introduce a couple vocab terms here, right? Um, there we go. Okay, so the plate boundaries are where the plates meet. And again, a tectonic plate is a large chunk of Earth's crust, of the lithosphere, really. A large chunk of the lithosphere that moves together. That's all it is. It's just a chunk of rock that moves together. Now, it's a chunk of rock that's sometimes thousands of miles wide and thousands of miles long. So when we say a large chunk, we're not talking about something the size of your house. We're talking about something way bigger. Okay. But it's just a big chunk of rock that's moving together. There are a lot of vocab terms that you're going to see here. There's divergent. Pay attention to the vocab, the prefixes and the suffixes. Thank you. Die on divergent. Die means apart, right? If we look at, did we skip convergent here? I don't know if we skipped convergent. No. Transform plate boundaries are ones that slide past each other. Okay. So they're transforming the earth around them. Divergent, right? Die means apart. Convergent, right? Con means together, right? That's where two plates are coming together. Well, two things can't occupy the same place at the same time. So they've got to move. And they move. Sometimes one goes up and the other goes down. Sometimes they just smash into each other and they both go up. Just kind of depends on their density and the rocks, the elements that make up those specific rocks, right? So lots of cool new vocab terms. I do not expect you to memorize all these words, but I do expect you to understand the basic concepts, that you do need to memorize divergent, transform, convergent. Okay. But and understand, when two things head in the same direction, well, they can't both be there at the same time, right? So they've got to go somewhere. Well, they can't go sideways on the earth, right? Because there's more rock that way. So they got to go up and down. Okay. So just think about it in practical, realistic terms, right? Divergent, they're splitting apart. Well, what's happening? They're leaving a hole, right? What comes up through that hole? Magma. More rock. Turns out the Atlantic Ocean is getting bigger by about an inch every year. And in 100 million years, Africa will be two different continents. It's splitting apart. All kinds of cool stuff that you can dig into here. And it all comes down to that one video we watched last week. All comes down to that one video we watched last week, okay? And then tsunamis. We're going to dig into earthquakes a lot later, but tsunamis happen. I believe that Orion mentioned this. Let me see if I can find the right slide here. But tsunamis happen when those rocks shift underneath the water. Well, there's thousands of feet of water above them. So if a chunk of rock thousands of miles wide does this, it moves up an inch. So there's thousands of miles of water wide and thousands of feet of water above it that are all going to move because of that. And that's how you get a tsunami. Okay. Let's do our exit ticket. We got to skip a lot of that stuff. So that's what scientists do, guys. We look at the data. We identify patterns and then we try to explain it. We're like, what's making that happen? It's really, really neat. Um, oh, here, let me give you guys. Nope, that's not what I wanted to do. Ah, just go down to the last slide here. Our exit ticket. I'm gonna put the link in here. Yes, I am doing that. I know, aren't they fun? I put the link in chat in case you're not in the pair deck. Thank you for coming. I loved you guys. Had some great observations in chat and vocally. Thank you so much, Lily and Adeline and Orion and Evie and Azalea. And I think Trey offered some really good ones. There were just some fantastic observations today.
Sorry,
Great
what was
job,
the
guys.
exit ticket? I was talking to my mom. Can I get it again?
Yeah. Oh, I haven't said the word yet. I'm so sorry. I keep forgetting. I keep getting distracted. The exit ticket today is going to be transform. Okay. It's going to be transform. That's our password, our passcode today for the exit ticket. Because we live right next to a transform vault, guys. Thank you for coming. Have a great day.
Bye. Have a blessed day.
You